we have derived this relationship between dx dy dz and dx dy dz and the displacement gradient tensor the first way, which is more mathematical. Now, we will derive the same relationship the more geometrical way in terms of the components of the total difference in displacement. Okay. I like to mention the book which is being followed here by Brady and Brown, rock mechanics and for underground mining, a very peculiar reference in the sense that this particular topic which I am going to discuss is done mostly mathematically in most of the books. Okay. I would appreciate certainly this book that is done more geometrically, and that is why I am following that approach. Okay. If you refer any typical book on solid mechanics or continuum mechanics, this particular step is done more mathematically. To be very specific, this reference is being chosen so that we get a good geometrical interpretation. Okay. What is that we are going to do? Derive the same relationship in an alternate way in a more geometrical sense. Okay. Now, and also look at the components of the total difference in displacement. The title has to be explained. First we had displacement, we said we want to eliminate translation. So, we looked at difference in displacement. Now, what is total difference in displacement? It just tells you that whatever 2 points and their total difference in displacement, which may be because of rotation, normal strain, shear strain. I do not include translation now because we are looking at difference in displacement, translation is gone. But still remember, this total difference includes that due to normal strain, shear strain and rotation. Rotation is still there. At the end of this, what we will see is, remember what we said was we want to eliminate both the rigid body motions, namely translation and rotation. We have taken care of translation very easily just by difference. At the end of this discussion, we will separate out rotation also. Okay. That is the whole overall picture. Let us go to the details. How are we going to do this? We are going to take a plate or 2 dimensional region. Plate is little more physical to imagine and visualize. Actually, it is a 2 dimensional region in a solid, and we are going to consider points P and then S. Why are we considering? The x distance between them is delta x, y distance between them is delta y, and that is what is shown here, delta x and then delta y. Why are we considering? Remember, when we derived the relationship for displacement gradient, we considered 2 points P and Q, and the difference in x coordinates was delta x, y was delta y, z was delta z. Remember, we are going to arrive at the same expression. So, here also I am considering 2 points, of course in 2D, which are separated by delta x and delta y. Now, 3 cases will be considered one by one. What are the 3 cases? The first case, I consider that the understanding will take up as a plate. The plate undergoes only normal strain, only normal strain. Look at the title here, the figure here. This figure shows only normal strain, and this title shows normal strain. We will come to the table shortly. Second figure, I consider only shear strain. The lengths are same, okay, and there is no rotation of the element, but there is only shear strain because there is change in angle. So, only shear strain, and the second column heading is shear strain only. Third, I just consider the rotation of the plate only, no normal strain, no shear strain, and that is a third configuration, only rotation. Okay. Now, what are we going to do? What did we say? Displacement is because of translation, rotation, normal strain, shear strain. We have taken care of translation by difference in displacement, which means that if you say difference in displacement along one direction, let us say x direction, that has components from normal strain, shear strain and rotation What do I mean by that? If there are 2 points and then there is a difference in the x displacement, which means that could be because of normal strain, could be because of shear strain, could be because of rotation. What you observe is a sum effect of all these 3 put together in terms of difference. We are going to dissect it, find out the components. Okay, that is exactly what we are going to do. That is why this table is a matrix where we are going to find out the components of the total difference in displacement. Understand why total difference in displacement? You have a difference in displacement, what you observe is total, it has its components, that is why I call as total difference in displacement. Okay, just want to mention that finally we will go back to differentials, because our relationship was in terms of differentials. Just for understanding, tentative will come to in terms of difference. If you look at the previous, we have used dux, dx. Instead of using dx, dy, dz, I will use delta here just for easy understanding, so that you can visualize a plate, etc. Okay. So, coming back, what is that we are going to do? We are going to find out the components of total difference in displacement along 3 directions. What do I mean by that? You take 2 points, you observed a difference in their displacement, that is a total difference in displacement, that is the heading of this row, that we are going to split into that the difference due to normal strain, difference due to shear strain, difference due to rotation, difference in x displacement due to all this, similarly difference in y displacement, similarly difference in z displacement. So, this table is going to be filled up in a more geometrical way. Okay. So, just to summarize, we are going to take a plate or 2 dimensional region subjected to normal strain only, shear strain only, rotation only, find out what are the components of the total displacement along x direction, y direction, z direction. Okay. Now, let us start with the earlier I said total difference in displacement. Look at the title now, difference in displacement due to normal strain only, that is what we are going to see. So, of course, now a larger figure is shown. We are considering the plate. Please note that we are considering a point P and a point S. The distance, x distance is delta x, y distance is delta y. This is in line with our earlier consideration of points P and Q separated by delta x, delta y, delta z. Now, the plate undergoes normal strain only. What do I mean by that? There is a change in the length along the x direction only. There is no change in angle. Okay, just want to mention this red is the original configuration or initial state. Remember, this is blue line, but below that you have a red line. So, whatever I mark now is the initial state, and then you subject this to normal strain only. So, now what is the boundary? The blue line is the new state. Okay. Part of the red is below the blue boundary. Now, subjected to normal strain only, and then along x axis only. Okay. Now, we know that normal strain is related to the displacement gradient in terms of dou ux by dou x. I will write in terms of difference epsilon xx is equal to delta ux by delta x. As I told you, we are working in terms of difference for understanding. So, I will write dou ux as delta ux, dou x as delta x. What does this tell you in terms of physical? If you want to read this statement, it tells you it relates normal strain to the difference in x displacement between 2 points which are separated by delta x distance. That is what we have here. We have 2 points which are separated by distance delta x, and so this expression should relate to the difference in displacements between P and S. Now, the point P, the way in which you have drawn, there is no displacement for point P. So, the displacement of S becomes the difference in displacement. Is that fine? We are considering points P and S. Point P, there is no displacement. So, actually S moves to S star. I should have noted here just displacement of point S only, but what is that I have marked there? Difference in displacement. What is the reference point? My reference point is P, because P there is no displacement of P, displacement of S becomes difference in displacement. Okay. So, please keep this in mind, this follows for all other discussion also. Though it may look like displacement, it is difference in displacement, because we are always considering point P which is for which there is no displacement. Okay. So, now we can, what is that we are interested in? Remember, we are interested in the difference in displacement due to normal strain only. So, same expression earlier we wrote as an expression for normal strain, but now we are going to write an expression for delta u x, which is what we are interested in. So, delta u x bracket normal strain only is equal to epsilon x x into delta x. Physically what it tells you is x to S star, the difference displacement or difference in displacement because of normal strain only can be obtained by just multiplying epsilon x x into delta x. So, once again this discussion looks like you have a plate and then of a finite length delta x delta y. Please keep this in mind, small region in a solid 2 dimensional region where these are very close to each other, P and S are very close to each other. For visualization we are drawing a diagram and then saying a plate etc. Remember, because epsilon x is a point definition as delta x into 0, delta y tends to 0. Similarly, here also these points P and S are very close to each other as we have as applicable to the definition of epsilon x x. Okay. And so, this gives you the difference in displacement, this expression gives you the difference in displacement along the x direction because of normal strain only, and that entry is made here. We have 9 entries to make, we have made 1 entry. Now, similarly, if you consider the y direction and z direction, we can fill 2 more entries. What we have, this table tells you is what is the difference in x displacement because of normal strain along x axis, y axis and z axis, and one component is now completed. So, now let us move on to finding out difference in displacement due to shear strain only. Now, same plate is considered. Now, the initial state is given by PQRS, the red boundary, and P star, Q star, R star, S star is the final state, the and the deformed boundary, and the way in which you have considered is you want to include only shear strain. So, there is no change in length, P r is equal to P star R star in terms of length. Similarly, all other sides also, and also there is no rotation. Look at the diagonal P s and diagonal P star S star, there is no change. So, only the change in angle has happened, no normal strain, no rotation. Okay. Now, of course, the length delta x delta y are shown. Let us proceed further to explain other nomenclature. Okay. We are considering the case of pure shear strain where there is no normal strain and rotation. Okay. Now, earlier we said this angle, okay, what I shown here is this is a diagram, part of the diagram which I used to relate the strains to the displacement gradient. Okay, I have taken a small part of that and shown here. We showed this angle is alpha, alpha made by P star Q star with x axis, angle made by P star R star with y axis beta. Now, those angles were different in a general scenario where you had rotation, normal strain etc. But now we have only shear strain, you can easily imagine it is going to be symmetric. I have only shear strain, and so this angle is alpha, this angle is also alpha. This happens only when you have only shear strain. If you have normal strain, rotation, which is a more general case, then one is alpha, other is beta, they need not be equal. In this case where you have only shear strain, it just changes in angle. So, alpha and beta are equal. Okay. Now, we defined shear strain as gamma xy is equal to pi by 2 minus r star p star q star, that is the angle between two perpendicular line elements in the initial state, which is 90 degrees or pi by 2 radians, minus the angle between those two line elements in the final state, and that is how we define gamma xy. That gamma xy was earlier alpha plus beta. Now, because beta and alpha are same, it just becomes 2 alpha, and hence alpha is equal to gamma xy by 2. Alpha equal to gamma xy by 2 is applicable when you have shear strain only, that is a relationship. Now, tan alpha, of course, alpha is very small, we are working in that limit. Tan alpha is equal to alpha. We already derived while discussing this case where we are relating strains to displacement gradient. We proved that alpha is equal to dou uy by dou x and beta is equal to dou x by dou y. You can refer those slides for this derivation. Now, for the present case, we will write in terms of difference. So, I write as delta uy by delta x for alpha, and now for this case beta is equal to alpha. So, written here again alpha and written the right answer in terms of difference, namely delta ux by delta y. Now, these expressions, first expression for alpha, second expression for alpha, correspond to this figure. Let me explain. Let us take this expression alpha equal to delta uy by delta x. What is shown here, this angle is alpha, this angle is alpha. Of course, when there is shear strain only is going to deform to a parallelogram. So, this angle is alpha, this angle is also alpha. So, all angles are alpha. Now, if you consider this triangle, you do not see a triangle there. Why? Because I have shown a large value of alpha. Remember, alpha is extremely small, 10 power minus 6 or such a small value. What happens? Then this r star s star can be approximated to a triangle. Now, of course, does not look like that, it does not look like even a triangle, but remember this is going to r and r star are going to be very close to each other, and then you will have s star somewhere here, then r star s star s will be a triangle, and then you can apply this relationship for that triangle relating alpha, delta uy and delta x. What does this relationship tell you? It relates alpha to the difference in y displacement for two particles which are separated delta x away. That is what we have here also. Once again, like last example, the difference in displacement is related to the point P, and that is why s to s star is displacement, but denoted here as difference in y displacement. Okay. So, this relationship is applicable for this case, and what is that we are in this relates alpha to difference in displacement and the distance between them. What is that we are interested in? We are interested in the in getting expression delta uy from this equation. Now, let us take the second relationship alpha equal to delta ux by delta y, and that corresponds to this triangle. Once again, in the limit of very small alpha, it becomes a triangle. The second equation, what does it tell you? How alpha is related to difference in x displacement between two particles which are delta y away. Same thing is here, we have p and then s which are delta y away. So, this equation is applicable for this triangle, and we are going to use this. We have written for alpha, but what is what is of interest to us is the difference in the x displacement delta ux, and that we will write this expression for delta ux. Okay. So, now we will write the difference in x displacement due to shear strain only. So, delta ux shear strain only is equal to alpha delta y. What is that I have done? Taken this equation, written an expression for delta ux, and the bracket says shear strain only, and what is delta ux is alpha delta y, okay, and alpha for the present case is gamma xy by 2 into delta y. Introduce another nomenclature which has to be kept in mind from now onwards, is that gamma xy by 2 shear strain by 2 is epsilon xy. Why is this nomenclature you will understand little later, but gamma xy by 2 is equal to epsilon xy. So, gamma xy is shear strain, half of that is denoted by another variable, namely epsilon xy. Okay. And what is the significance of this statement is that you had a plate, it subjected to shear strain only, then what is the difference in displacement? Delta ux is difference in displacement. What did we say? That this difference in displacement could be because of normal strain, which I already discussed, could be because of shear strain. So, we are saying that the difference in displacement that can happen because of shear strain in the x direction is given by delta ux, and that is what we have related to the shear strain gamma xy, of course half of that gamma xy by 2 into delta y. Okay. Now, similarly you can write the expression for the difference in y displacement due to shear strain only. See, when shear strain happens, there is not alone difference in x displacement, there is difference in y displacement also. You can very clearly see s moves to s star. So, there is a displacement in x direction, s moves to s star. So, there is displacement in the x direction, displacement in the y direction. Of course, we are calling it as difference in displacement related to p. So, difference in y displacement, what is that I do? I take this equation, okay, the first expression for alpha equal to delta uy by delta x. From that I write relationship for delta uy as alpha into delta x. Okay. So, I take this equation, okay, and write an expression for delta uy for shear strain only as alpha and delta x. As we have done in the previous equation, replace alpha by gamma xy by 2, gamma xy by 2 has another nomenclature, namely epsilon xy. What to conclude, what we have done is, if there is shear strain, what is the difference in displacement along x direction, y direction. Okay. Just complete for other directions. Okay. This expression which we have written in the previous slide, difference in x displacement due to shear strain only, difference in y displacement due to shear strain only. The nomenclature has been made very clear. Difference in displacement in the x direction, so delta ux. Now, we are considering not the total difference in displacement, we are considering only that due to shear strain only. That is why the within the bracket it is written as shear strain only. Now, let us fill up the table. Okay. Now, remember what did we say? Shear strain causes difference in displacement along x direction and y direction. So, you will have one entry for delta ux, you will have another entry for delta uy, that is what is shown here. You have one entry for delta ux, which is epsilon xy into delta y, another entry for delta uy, epsilon xy into delta x. So, these are the two terms which we have written based on the strain in the xy plane. We have considered xy plane, considered the strain which has resulted in displacement two directions, one in x direction and y direction. So, one entry should be here, another entry should be here. If you understood this very clearly, extend to other pairs of directions. For example, if you consider y and z axis, what will happen? You will have one entry here, another entry here. So, it will contribute to displacement along y direction and z direction. Now consider strain in zx plane. What will happen? You will get one component difference in displacement along z axis and another contribution will be along the x for the x displacement. Okay. So, strain in one plane xy plane for example causes difference in displacement along x direction and y direction. Okay. That should be kept in mind. Okay. That is of course, we just now discussed shear strain in the xy plane results in difference in x and y displacement.